All right, so this is the cryptography class. We're up to chapter 6. Let me make sure I'm in the right class. I was in the wrong class once last week. This is the Monday class. Good, okay. All right, so chapter 6 is hash functions. Let's take a look at that. And here it is. All right, so we're going to talk about secure hash functions, how they work, the SHA family, and the newer one, Blake 2, and then usually some things that can go wrong. So a hash function lets you put a fingerprint on a digital object of any size. And the point is you can use it to identify if that object has changed, and you can make digital signatures. You can sign something. Public key encryption uses hash functions. Almost everything on the internet does. And you can do password storage and password generation. Password generation is done with hash functions where you key generation from a password, and you store passwords by hashing them, because then it's hard for someone to steal the password because of the preimage resistance, which we'll talk about. If you have the hash, it is very difficult to find the input that would create that hash. That is called preimage resistance. So, and simplest. What's that?
How does pass the hash work?
Oh, pass the hash. Pass the hash is when you log into a Windows server once, then you connect to other servers on the network. It has to know who you are, and it verifies who. It could make you type in your password again, but instead it just sends the hash over the network, and it takes the hash as authorization that shows that you have logged in. So the pass the hash just steals that hash off the network, and then you replay it without decrypting it.
Oh, because other websites accept the hashes?
Yes. And this is the problem with all single sign-on systems. You sign on once, and then you get a token like a cookie, and now the cookie will let you in other systems. So if I can steal the cookie, I can impersonate you.
The attacker has to be like hit a lot of websites to get lucky.
Well, the pass to hash usually works by tricking you into sending the hash to the attacker. You run a tool like Responder.
But the attacker, after they get the hash, they will try it on different websites.
They have to have access to the network. So typically they'll compromise some machine on the network and start sniffing the network. Then they'll run Responder, which pretends to be a network file share. And then they trick people into trying to connect to the file share, and then their machine sends the hash over to authorize. That's how you do it. Or you compromise one machine and look in the memory of that machine for the hashes. That's the game. This is why the thing about pass the hash is you do not need to reverse the hash. You can just use it as an authentication. So they never actually get your password, but they don't need it.
Just like cookies.
Yeah, just like a cookie. Yeah, very good. All right, so now what a hash function does is it makes a fixed length fingerprint. So you can put in a message of any length, run it through the hash function, and you get a short length, like 256 or 512 bits. It is not encryption. It cannot, in principle, be reversed. And in principle, it destroys information. I can put in stuff that's longer than 256 bits, and then I get a 256-bit fingerprint. So clearly there's no way to go back. It's not intended to be encrypting things so you can decrypt them later. It just is a way to put a fingerprint on something to identify it. And therefore, in principle, there always are hash collisions. There are more possible messages than there are possible hashes. If you have 256 here, there's only 2 to the 256 possible hashes, but there's many more messages than that. If this is 1,000 bits, I have 2 to the 1,000 of those. So in principle, there are many messages that hash to the same value. So when you say you need a hash function that doesn't have collisions, what you mean is you have a hash function where no collisions have been found. And the collisions are so rare that we don't imagine any will be found anytime soon. So like everything in this whole course, the mathematics of cryptography sounds great, and what it really is not that great at all. It's just a estimate that it's good enough for a while, and we project it'll be good for a while yet. It's not at all as perfect and beautiful as you might hope it would be. There are hash functions that provide no security. They've been around for quite a while, like CRC. Cyclical redundancy check was added to layer 2 of Ethernet because, especially in the early days, like 40 years ago, you'd be sending your traffic down a wire, and there's a possibility that there'd be like radio noise, and that wire would drop a bit. So one bit would be missing from the packet when you went in. So in the early days, you used parity. Every byte had 7 bits of data, and the 8th bit was the parity bit, and the total number of ones had to always be even or odd. And that way, if you drop 1 bit, you can tell that it's happened and discard that and resend it. That was the original plan. This is why ASCII only uses 7 bits in the byte. The 8th bit was for error correction. Now, Ethernet came later when networks were faster and better, so they added a cyclic redundancy check, which is a 32-bit hash to each packet. Each frame, I should call it, at layer 2. Then you calculate the CRC of the frame and compare it to the value that's sent, and if that fails, then you know that frame was damaged in transit. So that's all it's for, but it is so short that you can easily forge messages with any CRC32 you want. It will not stop an intelligent attacker trying to trick it. It will just catch random errors made by the electrical flaws on the line. There's another kind of hash table too, used in computer science, where if you have a table of information and it's related of data that's used for another part of the program, it is better to, like if you're going to store data, you have a whole bunch of things coming in, you're going to store them in a big table. You don't want to put them all in the same place in the table. You want to make it possible to do parallel processing and so on. So you want them to be evenly dispersed through the table. So they often use a hash function just to create a pseudo-random number to put it randomly in the table. That way you can look it up again by using the hash function and it's evenly using the table. This makes operations more efficient on computers, but again, that's not cryptographically secure. That hash function is just there to have an organized way to sort of randomly sort things into categories. It's not intended to survive a deliberate attacker that would try to manipulate the data to trick the hash function. So that's a thing to be aware of. Same thing's true of random numbers, like we talked about before. There's a bunch of pseudo-random numbers which are good enough to, say, play a video game, but they will not survive an attacker. There are ways to predict them, ways to fool them. So secure hash functions are what we're most interested in. These are things good enough to use for cryptographic purposes like digital signing. So you have a message, and you want to put a signature on the message. What you typically do is hash it first to make it smaller, and then you can do the signature function. This is what's typically done with all digital signatures. You have your message, you have a hash, and then you insert a private key and create a digital signature, which proves that you own the key because anybody can verify with the public key, and it proves that the message has not been altered because they can recalculate the hash and make sure the hash has not changed. So as long as the hash function has no known collisions, or technically as long as it has pre-image resistance we'll talk about, then that proves the message has not been altered, and the fact that the signature verifies that the public key means that you're the holder of the private key, so it proves that it was signed, unaltered, and that you signed it. And this, due to the Digital Millennium Copyright Act of 1998, this has the same legal force as a signature with a pen on a piece of paper, and now you can do financial transactions on the internet because this digital signature has the same force of law. So, your hash should be unpredictable. If you change anything about the input, the hash should just change randomly. You can see SHA-256 has that property. If I do A, B, C, these only change one bit at a time here. And you see, you change one bit from A to B, and everything changes all over the hash. That's what you want. The whole thing should change. There shouldn't be any pattern where changing this would change just a couple bytes at the end. Like, that would be bad. That would give you a weak spot to attack. That's unpredictability. Then there's non-uniqueness. Like I say, if you have 10 to 24 bits coming in and a hash 256 bits long, then obviously there are many messages that hash to the same value because there are more total messages than there are to hashes. So it is not a unique transformation like cryptography is. If you encrypt something with AES, you make an answer and it can be decrypted. There is only one message that will create that encrypted message, and therefore you can get back to it. But in principle, you could never reverse a hash because there are many messages that would hash to that value. So there's not a unique transformation to go back. Now, by the way, in practice, there usually is, because you hash something like a password, and there's really only going to be one message that is of a reasonable length and using printable characters and things like that. But in principle, it's not a unique transformation back. And so that one-wayness is another property you want. You want it so they cannot reverse it. That's the point of it. If they could reverse it, it might be a function good enough for some things like CRC32, but it won't be good enough for cryptography. So you want to make sure that if they know the hash, they can't figure out the message. And this is why you hash passwords when you store them. If people steal the table of hashed passwords, it's not easy to extract the real passwords from that table because of this one-way property. And this is the one I talked about before, pre-image resistance. This means if I have a hash value and I realize it's not unique, but I would like to find a message that hashes to that value. This, by the way, would be good enough to log in. If your login stored a hash and I found another password that had the same hash, it would accept that. It doesn't know. So this is called pre-image resistance. If I know the hash, can I find a message that will create that hash? And you should be resistant to this attack if you want to be a strong cryptographic hash function. And there's a second one. Well, so we can figure out the cost of this. So if you want to find a match, then if you have n bits, you're going to have to do 2 to the n guesses to catch that particular value. So if I have a certain hash value, I'm going to have to try messages at random until I hit that value. Well, typically I'll have to try as many as there's bits in this. It'll take 2 to the n guesses. So if you have a 256-bit hash, that's forever. 128 is also forever. 2 to the 128 and 2 to the 256 are more calculations than you can ever make with all the computers in the world for all the time in the world. So that's why a hash of 128 bits or longer should be strong enough that that nobody will be able to find from the hash an input that will create that hash. Then there's the second preimage. So once you have a message and a hash, they want to find another message that hashes to the same thing. That's called the second preimage. And that's essentially the same as the first one. And the only reason why this is worth even talking about is because there is a category of hash functions that are particularly vulnerable to second preimages because there are length extension attacks. And almost all the ones we use are vulnerable to this attack. This is how you make hash collisions. You can't do a first preimage. For example, with MD5. MD5, you cannot do the preimage. It would take 2 to the 128 calculations to find a input that will come from the hash. But once you have one message in hash, you can easily construct a second message with the same hash. Or to be fair, if you have one message in hash, you can easily construct a pair of messages that will hash to the same value because of the extension attack, which we'll talk about. That's why this is a very commonly misunderstood situation. Decades ago, people figured out how to make MD5 hash collisions, and a few years ago, Google made a SHA-1 hash collision. So they constructed 2 inputs that had the same hash, and people said, there, that hash function is useless, don't use it anymore. And well, that's not a bad thing to do, because you don't want to explain this complexity to like a judge or an attorney in court. But the fact is, even though they were able to generate a collision, that does not mean you can break the preimage. So for example, if you do a forensic image of a hard drive and then you put an MD5 hash on it, the fact is that is perfectly fine. That MD5 hash means that if you make a copy of that file and calculate the MD5 hash and it matches, you have great confidence that that copy has not been altered, because even though in principle there are collisions, finding another input that has the same hash value is still impossible. Even though you can generate hash collisions, that is not the same thing as preimage resistance, not even close. Anyway, so here's every hash function has collisions in principle, but you hope that it won't find. It's a pigeonhole principle. If you have 10 holes and 11 pigeons, that means there's one hole with 2 pigeons in it. But you hope you can't find them. So they should be hard to find, in practice impossible. That's what you call collision resistance. So, and to understand this is the birthday attack, this is a common classroom thing. If you ask everybody to give the month and day they were born in a classroom, you'll find 2 students have the same birthday, even when there's only like 30 people in the class. That's because even though there are 365 days in a year, the probability of any 2 of these matching, the first one could match the second one, the first one could match the third one, the first one could match the fourth one, the second one could match the third or the fourth one. So there are many more possibilities of 2 of them matching than just 23. It's more like 23 squared possibilities. It's actually 23 times 22 over 2 pairs of students, and that means there's a lot more chances of 2 of them matching. And so it is, in fact, with 23 people, you have more likely than not that 2 of them have the same birthday, because you didn't specify the birthday. Now, if I picked a day, like January 1, and said, is anybody out there born on January 1, that is the preimage resistance attack, and now I'm going to have 180 students before somebody's likely to have that particular date. But for any 2 of them to match, that's a much more vague condition and much more likely to be answered. That's what I'm saying. You can generate a hash collision for MD5, but you cannot generate input that will hash to a particular value, which is what you would need to forge a forensic image based on the hash or any other file. So, all right. So anyway, if you want to find these now, if you want to find a collision, all you have to do is 2 to the n over 2 hashes, the square root of the total number of hashes, because by then you'll have approximately 2 to the n pairs, and you'll have a likelihood of finding a hash. So if you have a 128-bit hash like MD5, you only need to do 2 to the 64 calculations to find a collision. All right, so this is the naive birthday attack. Compute 2 to the n over 2 hashes of any messages, then just sort them and find 2 consecutive entries at the same value. So if you can do 2 to the n over 2 calculations and you have 2 to the n over 2 units of storage, then you can do this. All right, and so if you consider a simple example of MD5, so the pre-image attack, MD5 is 128 bits long, so if I give you a hash, can you find an input with that hash value? And the answer is no. You would have to do 2 to the 128 calculations. You have to feed in that many inputs to finally find one with this hash, and that's more calculations than you can ever do. You don't need to store them all. You don't need the memory. You're only going to calculate one and see if it's right, and if not, throw it away. So you don't need to store them all, but you do need enough processing time to calculate them all. And so the question is this an impossible number? And the answer is yes, and here's why. RSA Security made some challenges to test brute force attacks. They've been doing it for 20 or 30 years now. They cracked a 56-bit key in 97. They cracked a 64-bit key in 5 years. A 72-bit brute force attack is still in progress. It's been going on for years, and it's expected to take more than 100 years to crack a 72-bit key by brute force. Now, it's not going to take 100 years because that would be 100 years at the starting rate, and computers keep getting faster. But it's still going to be a long time. And so that's nowhere near 128. However, you can ask what is the power of all the computers in the world, and now we have a nice answer, which is Bitcoin. Bitcoin pays people a lot for doing calculations, so if you take the entire global Bitcoin hash rate, it made it up to 2 to the 93 hashes per year. So that is essentially the total computing power of the entire world. They made the very fastest machines and ran them as fast as they can, competing to make a lot of money, highly incentivized. So if you were able to take all the computers in the world and run them for a year, you could do 2 to the 93 calculations. All right? Now, so the maximum calculation available to any attacker is, say, 2 to the 96, just to get a sort of rounded number in a year. The pre-image attack requires 2 to the 128, so that is more than 2 to the 30 times as long. 96 plus 30 is 126, so I dropped the 2, I don't care. So our safety margin is 2 to the 30. And 2 to the 10 is 1,000, so that is 1 billion. So it would take 1 billion years to perform a pre-image attack on MD5 with all the computers in the world. So that's pretty safe. So that's the kind of math you use to calculate it. And so if you were to take, if you want to find a collision, though, with the birthday attack, then you only need to do 2 to the 64 calculations, calculate them, store them, and then find the duplicate. So what's the safety margin here? And the answer is 2 to the 64 is not impossible. We already said a 64-bit key has in fact been cracked by brute force. So you can get computers that can do that many calculations. How about 2 to the 64 bytes of storage? Well, that turns out to be 16 million terabytes, which is 16 exabytes, and the total storage in the world is 2,500 exabytes. So if you had powerful computers, this is not impossible. If you had a large portion of all the world's processing power and a large portion of all the world's storage, you could make a birthday attack on MD5. So you could perform the naive attack, and you could, by brute force, find an MD5 collision. However, that is not a pre-image attack yet. So you just find a collision. There are much easier ways to find a collision with links extension, but anyway, it still doesn't give you the pre-image. And like I say, the pre-image attack is totally out of reach. So we could continue to use MD5 as a fingerprint of a downloaded file. The only reason we don't is not mathematical, but psychological. People say, oh no, MD5 is broken. You can't use it. You don't want to have that argument, so you use SHA-2. All right, anyway, so if you want to find a collision and you want to find it without having to store some huge amount of products, then you use the row method. So instead of just taking inputs like 1, 2, 3, 4 and hashing them, you hash from seed, and then you hash the hash and hash the hash. This is the trick. We talked about it before for the project. And so now you have this kind of pattern. This hash is to there, this hash is to there, this hash is to there. Eventually, you'll have a collision where something else hashes to the same value. And typically, the length of this tail is the square root of the number of possible hashes, and the circumference around this circle is of the order of the square root of the total number of possible hashes. So this is what's going to happen. And therefore, you don't have to remember all the hashes. You can pick particular hashes to remember, like the ones that start with a certain number of zeros. So you don't have to have enough memory to store them all. And so you might calculate this one, but you don't save it. But somewhere on this loop, there will be one that passes your test, and you remember that one, and you'll eventually hit it again. That's the trick. So you store the distinguished points, and therefore it'll take you a little more time. You might have to make up to one extra circle around this loop of time, but you save a whole lot of memory because you don't remember all the hashes, you only remember the distinguished ones. So that's a time-memory trade-off, and that's the row attack. All right, so, and you've done it in the projects. We had some simple Python. You can do it for hashes of various sizes, and we talked about that before. And you see, this is what happens. This hash function is 1 byte, so it is an 8-bit hash. So there are 256 possible hash values. So the square root of that is 16. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. This is 10. This is 14 across. So about 16 hashes in, you hit the loop, and the loop is about 16 hashes long. So this is what I'm showing. The tail is about the square root of n in size, and the loop is about the square root of n in size. So you can see for this short hash, it obeys the general principle of the row method, and they all will obey that. So let's try a Kahoot. All right, which is going to be here. All right, and this is chapter 6. I don't need to keep using it. I think I might have put it in my favorites. I didn't. All right, let me do it this way. I thought I might not need to use my favorites, but now it occurs to me I might. Because there's these, one thing about this thing is it doesn't sort things very nicely. There we are, 6A and 6B. It's not too bad. All right. It has cute images and music, though, despite not sorting the data. Ah, 15 people online, okay. Give it another few seconds, but I think this might be all we have. Apparently so. All right, so which hash functions have collisions in principle? All of them must have collisions. It's just that we can't find them for SHA-3 yet. All right. All right, how many calculations will it take to find a message that hashes to a specific 32-bit hash? Yep, 2 to the 32. As you might imagine, you have to, that's how many possible hashes there are, and you have to try that many calculations before you have likely to hit one of them by luck. All right? How many calculations will it take to find a hash collision for a 32-bit hash? You got it, 2 to the 16, a much smaller number, because once you've calculated 2 to the 16 hashes, you have approximately 2 to the 32 pairs that might match. All right. All right, what method uses more RAM but less CPU? That's the rainbow table attack. Rainbow tables are where you pre-calculate something and put a big table in RAM so you use less CPU. You look things up. It's used for a lot of things. It's used to crack Windows hashes. It's used to calculate AES. We talked about it a couple chapters ago. So that's what rainbow tables do. More RAM, but saves CPU. What method uses more CPU but less RAM? That's the row method, like we said. You don't have to remember all the hashes, but instead you'll have to do more cycles of computation. All right? Okay, what method uses more RAM and more CPU? That's blockchain. That's why it's fundamentally stupid and it's falling into disfavor. Instead of having one database, you have thousands of copies of the same database doing all the processing and all the storage over and over again. What you're gaining is escape from political and legal control. And you're paying a very high technical cost to achieve that. All right. All right. There we go. All right, good. So let's go back to the next bit of this. All right, so to build your hash function, how are you going to do it? Typically, you do it with blocks, just like the cryptography we talked about before. And so you process block after block, either with compression or permutation. I'm just lowering this thing, it's irritating my eyes. All right, so here's the compression-based function called the Merkle-Damgard instruction. This is how almost all of the ones we use work. So you start with an initial value, H0, and then you feed in a block of message and compress it, and that creates an output. You use that as the input for the next one, put in another block of message and compress it, and so on. It's just like cipher block chaining that we talked about before. So that's how it works, and therefore you can put in as long a message as you want, and you put in blocks of message, adding more blocks until you run out of message, and you end up with one hash function. All right, you might have to pad the last block, just like every other block-based things. You might not have enough message to fill this block, so you'll have to pad it. And they have, as always, a padding system. You put in a 1, then you put in some zeros, and at the end you put in the length of the message so it can remove the padding later, or at least understand what part of it was padding. There is no issue of removing it later because you never reversed this process. But anyway, that's the padding system that's used by these hash functions. So to build it, you can do it with a block cipher, for example. There's no reason you could use AES or something. You feed in the message, use it as the key, encrypt this hash value, and then you put an XOR function here to mix the value before encryption with the value after encryption, so that even if somebody finds a way to decrypt it, they won't be able to get there because the data they have is not equal to the normal encrypted value. That's the idea, to make it stronger. All right, there's other compression functions. There's a bunch of them. Use different mixtures of these things. Use the message both as the key and you XOR it here. You also have an XOR here. You can put the message there. There's lots of different ways to do it. They're less popular than the other construction. All of them are in principle strong. All right, then there's sponge functions. And this is what SHA-3 uses, a different philosophy. There is no key. And what it does is you have the original message comes in, you have an initial state of the thing, you XOR it in here, and then you permute it, mixing together, then you put in another block. This is called the absorbing phase. So you absorb all the bits of the message into it, and then you squeeze out a hash later. So just like a sponge, you feed in your message until it's swollen and wet, and then you squeeze out some hash bits after it's over. That's the way it works. So it's a different general philosophy. All right, So the SHA family, the most important to us, almost nobody uses MD5 anymore because it's had collisions for a long time and fallen into disrepute. So we had the whole reason we made the SHA function. MD5, by the way, was never officially approved by NIST or the government for any purpose. They didn't know we needed hash functions. MD4 and MD5 were written and people started using them. The government wasn't in the business of certifying cryptographic functions, but then they made DES, and they said, well, we really do need to have official government-approved cryptography functions, and they didn't approve MD5. Instead, they developed SHA, the secure hash algorithm. And first, so MD5 had been broken, like we say. It can't be reversed, but there are collisions. So SHA is what they approved in 1993. It was later called that SHA-0 because it turned out to have a serious defect. It only went 2 years. So they never told you what that issue is. They said something is terribly wrong with SHA-0, so they replaced it with SHA-1 in 95. And that became the standard, and almost everybody used SHA-1 until just a couple of years ago when they finally moved up to SHA-2. It's 160 bits long as opposed to the 128 bits in MD5, so they thought that would make it a lot longer. Now it would take 2 to the 80 calculations to find a collision, and especially back in the 90s, that seemed like a really big number, and they thought we'd never be able to do that. And as I said, a 72-bit key has never been broken by brute force. So if it really took 2 to the 80 calculations to find a collision, then there wouldn't be any SHA-1 collisions. The problem is they found attacks that broke it somewhat, got it down to 2 to the 60, and they finally got it down to 2 to the 33 for SHA-0. SHA-1, they didn't break it that far, but they did break it. So this uses an encryption function called SHA-cal. You do the encrypt, the message, and the hash, the internal state, and that gives and add it here, and that's what you do. For every 512-bit blocks, you keep adding the encryption and go through cycles like this. So it's the same as that diagram you saw before. You add a hash, add a block of message, another block of message, another block of message, until you get the final hash function. And so this is the compression function they use. You take your 160-bit value and break it into 532-bit words, and then you have this mesh where you mix the words together. This should look kind of familiar. You talked about this sort of thing before. Anyway, in 2005, they found an attack that would crack SHA-1 in 2 to the 63 calculations, and Google managed to break it. In 2017, they made a SHA-1 collision. There were 2 PDF files you could download, and they were both hashed to the same SHA-1. So that was considered the end of SHA-1, although, as I said, it really wouldn't have to be, because the existence of a collision does not mean you have fail to have pre-image resistance, but anyway, it means people don't trust it anymore. So SHA-2 had already been approved by this time. They saw this coming. Well, I guess I'm not sure about the history. They might not have done it until after it was broken, but I think they already had SHA-2 coming. So SHA-2 has 4 versions with different lengths, the most common being 256 and 512. So it uses 8 32-bit words, 64 rounds of calculation with a more complex function, and is overall generally similar to SHA-1. It's just a little more complicated, but the same general logic and structure as SHA-1. And that's why people are worried, because SHA-1 turned out not to be as strong as they thought it was, and SHA-2 is really not that different. It has not been broken yet, but there is concern among cryptographers that SHA-2 might have a flaw similar to the flaw in SHA-1. And therefore, they did the they did the contest for SHA-3. So we have a function approved in case SHA-2 is broken. So they had a SHA-3 function for several years. Mathematicians sent in all their functions, and Blake was one of the competitors, but the one that won was Keycheck. And as I said before, the finalists in each of these contests are all perfectly fine. And so if you are a person that does business with the U.S. military and government, you use the approved one. And if you are a rebel and you don't like the government-approved things because you have a bad attitude about the NSA and NIST, which is quite understandable, then you use the unapproved ones, which are just as strong but not the ones officially approved by the government. So Keycheck is the one that won. It's completely different. It's a sponge function, like we say, this step of absorbing the data and then a step of squeezing out the hash. And it has 2 extendable output functions too, called shake 128 and shake 256, that can produce the hash of any length. Since they had this sponge process, they can just squeeze out as many hash bits as you want. And these numbers here are not the size of the hash. This is the cryptographic strength of the hash. This one has a cryptographic strength of 128 bits. This one has a cryptographic strength of 256 bits, just like AES. That was in the specifications the government requested. We want a normal security one, which we regard as unbreakable, and we want another high security one, twice as long, which for highly secret stuff where people want more security. That was just like AES has these two sizes. This also comes in various sizes. And Blake 2, like I say, was one of the runners up and is largely, arguably, mathematically the superior hash function. It's as secure as SHA-1, but faster. And so it has one version optimized for 64-bit platforms and another version optimized for 8 to 32-bit platforms. And if you look at speed of calculation, it is fastest to calculate Blake 2. Here's SHA-1, here's SHA-512 and SHA-256, and here's SHA-3, 256 and 512. And you can see the SHA-3 is much, much slower than Blake. So that's why probably we should all be using Blake, but this is the one the government gave the seal of approval to. And in fact, many people are still using SHA-1, although I think SHA-1 is being deprecated gradually and everyone's moving to SHA-2. All right. And so it's the fastest secure hash available, the most popular non-standard hash. Many apps do use it, like OpenSSL and Sodium, which we'll talk about in the projects. Sodium uses all the best, most modern algorithms, and it's easy to use. A Python library, it's also ported to many other languages. That's why if you're designing any new product, what you should do is use Sodium. Sodium is carefully designed to be easy to use and to choose the most secure choices for all the parameters, so you don't really have to figure them out yourself. It is there so that normal people can write apps and just use good cryptography. As I mentioned, when I audit Android apps, people don't know how to use cryptography. They use it wrong. So they wrote the Sodium library to make it easy. And let me just point out that project. That's an important one, quite practical for this class. Let me go to this browser. If I go here to the projects, in here I put Sodium. There we are. So you can if you use the Sodium library here, it will automatically use the most advanced modern tree, and it's very easy to use. So if you want to design some cryptographic product, this is probably what you should do. Now, you could use RSA and AES and stuff, and then you'd have to be careful not to make the mistakes people usually make with RSA and AES. But if you want to be modern, just use Sodium. That's what it's there for. And it's carefully designed to automatically choose the right length of the key and the right length of the IV and the right number of cycles and everything else that you might be behind adjustable. It automatically chooses the recommended values for all those things. So this is what the cryptographers of the world would like us all to just use Sodium. And don't try to think about cryptography. Just use it. Don't make up your own. Don't try to implement something like RSA, for God's sake, where there's a bunch of obscure, weird problems you can do and get it wrong. Just use this library that carefully implements it correctly. So anyway, and that uses Blake, like I say. All right. So Blake compression function. You have a counter and a flag, and it's got a block cipher based on Cha-Cha, which is based on Salsa. These are all the modern ones, more modern than the ones that are officially approved. And so here's the compression function. You have the state coming in, the message coming in, and then two layers of these XORs here. All right. And so here's the core operations like the others. You transfer the state into 464-bit words and 2 message words, and then you just do the same kind of thing you've seen in AES and everything else. You do XORs and bit shifts right and left for different values, and that's how you do it. These are all chosen to be fast on a processor. The right size of the words, cryptographic operations that are quick, are easy for the computer to do, and they just scramble the bits up in a way that is hard to reverse. So, how things can go wrong. If you use a weak algorithm like CRC32 instead of a cryptographic hash algorithm, that's ridiculous, and that's like having a default password on your app. If you use the wrong hash function, then of course it's not strong. The link extension attack is the big one I talked about. If any of these things using the Merkle-Damgard construction, you feed in a block of message, and here's a hash of that. Then you put in the next block of message, and here's the hash of the longer message, which is M1 followed by M2. So if I have a known hash, I can add another block of message to it and create this hash from that one, even though I don't know M1 and M2. I don't know these messages, but I have this hash. I can create another valid hash for a longer message by adding an M3 here. And so that is a strange weakness. And that means I can use this hash function to generate that hash function for any M3 as long as I want. And that depends on how an application interprets me sending a hashed message. And there are applications where me generating a message that's valid is interpreted as authorization. And I could add extra data here under my control. So it might do something like verify the hash and say, there, that proves that you're authorized. And I can add all kinds of data here, which will interpret as commands. That's the sort of thing. So SHA-2 is also vulnerable, which is kind of a defect of the process, because at that time they knew about the length extension attack, and they could have changed it, but for some reason they failed to do that when they approved SHA-2. The simplest thing, by the way, to prevent this is to use a different compression function for the last stage. Add message, but at the last step, use a different function. Now I won't be able to add any more after it. It's a simple solution, but it was not implemented for MD5, SHA-1, or SHA-2. In retrospect, that was probably a mistake, but you know, SHA-2 is now the official approved standard. All kinds of gadgets have been built using it. You can't change it now, but what you can do is go to SHA-3, which doesn't have this problem. So, all right. So if you want to fool it, for example, here's an example attack. If a cloud server like Dropbox, you send up a file, and then to verify that it stored it, you can send a challenge value, and it will send you a hash back proving it has the file. That would be one possible thing, but what you could do is it could just keep the hash of M and throw away the file, and then when you send it a challenge, it could use link extension to generate this hash, so it could lie to you and tell you it stored the file when it hadn't. So this is a logical thing you might do with a hash function, is prove you have the file, but it doesn't in fact work. And you can see how this would also affect challenge login systems and such. That's the problem. All right, so that's one of the many flaws about length extension. And of course, the cure is put the challenge before the message instead of after the message. So you send it a challenge, it has to calculate the hash of challenge followed by message. It couldn't do that unless it had the whole message. You can't do that with linked extension. Anyway, all right. And actually, this says linked extension works with SHA-3, which is interesting. And I guess I'm not quite sure. By the way, nobody's using SHA-3 yet. I had some projects where people implement it. You have to download weird libraries. There are no products of any kind I know that are actually using SHA-3, because as far as anybody knows, SHA-2 is good enough. But for this slide, it says SHA-3 is still vulnerable to link extension, which might be true. I haven't checked into it. I thought it was not vulnerable, but the only thing he says is not vulnerable is Blake 2, which is probably why you may have noticed that book. They always say the new stuff is really better. So anyway, let's try another Kahoot. So that would be another reason to go off the reservation and use the unapproved functions, because technically they are superior to the approved ones. But I don't think you want to do that unless you are not interested in selling to the military or the government, because they would want everything to be standard. Slower is better for hash functions. Oh, yes. Luca has a good question. Yes, if the purpose of your hash function is to conceal a password, then you would want it slower. You're right. But for an all-purpose hash function, you want it to be fast so you can quickly calculate the hash of an MP3 or something. And then if you want it to be slower, you do many rounds to slow it down. So, I mean, you want the intrinsic function to be fast because it's easy to do many rounds to make it slower. There's no way to make it faster. So it is a defect that SHA-3 is so slow. That's going to waste a bunch of processing cycles. If we use Blake 2 instead, we just need less processing cycles for many common hash functions. Yeah, it's a good question, though. I had the same immediate response. Well, I want it to be slow for hashing passwords, but that's just one use case. To verify file integrity, you want it to be fast. All right, let's give it a shot. All right, so what hash uses a sponge function? SHA-3 does. I don't know what RIPE-MD does. It's one of those really old ones. But anyway, SHA-3 has this sponge function where you swell it up at the message and then squeeze out the bits for the hash. All right, which hash uses Merkle-Damgard construction? All of them. All three of them use the same construction, block by block. That's why they're all vulnerable to the same link extension attack. All right, which hash uses keycheck? Which I think is the name of the mathematician that invented it. Oh, I'm not really sure. That's SHA-3, is keycheck, okay? All right, what hash collision was found in 2017? SHA-1. That was when SHA-1 was considered broken and we were all told we better move to SHA-2. All right, which one is the fastest? Blake, by far the fastest, probably the best, but not officially approved. All right. All right, let me stop this recording.